Welcome to Winning Edge. Today we will discuss solid state. As you know, today we are using tremendous amount of digital technologies based on electronic devices, and all these electronic devices are made of basic semiconductor materials. Do you know that silicon that we'll use to make chips or any other electronic component is basically a purified form of sand? We see glaciers which are in solid state. They melt. You see here tremendous colors in the glaciers. We having these flying jets. The engines of jets and their turbine blades are made of special materials known as single crystal materials, having a very high strength at high temperatures. And there are many more applications that are based on different properties of materials. Study of those materials today falls under solid state branch. So let's try to systematically understand. Now, very first question, what makes solids? Why they are not liquid, gas? The answer is, the state of a given substance depends upon the net effect of two opposing forces. Those are, first, intermolecular forces that try to keep atoms and molecules together in a unified structure. Second force, is thermal energy that tends to keep them apart by making them move faster, as supplied heat will increase the average energy of the atoms or molecules in a structure. So balance between these two forces help us to understand whether at a particular temperature given substance will be a gas, liquid or a solid. That's what we saw. Thermal energy tried to put them apart. Intermolecular forces try to hold them together. Stronger the intermolecular forces, higher the energy required to make these molecules having a higher kinetic energy to overcome those intermolecular forces and move from solid to liquid and from liquid to gas. So it's a net effect of these two forces. At a sufficiently low temperature, the thermal energy is low and the intermolecular forces are strong enough to bring them close or in a solid state. Now, these solid substances can be classified broadly into crystalline solids or amorphous solids. These are based on the basis of nature of order present in the arrangement of their constituent particles. These constituent particles can be molecules, ions or atoms. Now, in crystalline substance, crystal having a definite characteristic geometrical shape. Here what we see, it can be cubical, it can be hexagonal, or it can be having these diamond sort of structures. Next is arrangement of constituent particle have long range order, which means a geometry that repeats itself is significantly over a longer distance. Same pattern you see is followed on a very long distance in a structure of such solids, crystalline solids. They have a long range order. Next is their melting points are very sharp. For example, we having a crystalline salt. We heat it up at a, let's say its melting point is 200 degrees Celsius. At 180-99, it will not melt, but certainly at 200 degrees Celsius, all of that salt melts to give us liquid state. So they have very sharp melting points. We heat it up, and suddenly the whole solid turns into a liquid. It melts. Crystals from different directions. So we are getting a crystalline solids are anisotropic. Like looking at a crystal which is structural geometry from different angles, we having a different arrangements possibilities depending on the angle. Like we see it from this angle or we see from this angle, our look, what we look at will be different. Like from here you see only one particular constituent atoms. From this angle you see different sort of arrangement. So from different angle, crystalline substances are not the same. The arrangement doesn't look the same. That's why they are called anisotropic. They are not isotropic in nature because of constituent particles having a different arrangement from different angles. See, from this angle it's different, from this angle it's different.